Welcome to Pomodoro Joe for Tuesday, February 28th, 2023. Today we'll be doing LeetCode problem 652, find duplicate subtrees. This is a medium one. So, given the root of a binary tree, return all duplicate subtrees. For each kind of duplicate subtrees, you only need to return the root of one of them. Two trees are duplicate if they have the same structure with the same node values. And here's some examples. All right, and some constraints. Node values are between -200 and +200, and number of nodes will be between 1 and 5,000. Okay, so with that, we'll put 25 minutes on the Pomodoro timer and get started. So normally with binary tree problems, I like to go with a recursive solution, but in this case, I don't think a recursive solution will work because we need to compare two different trees. So we could say like root, get left, get right, compare those, but we need a recursive call that takes two trees. So in this case, I don't think I can do a purely recursive solution just based on this find duplicate subtrees. However, we could do a recursive solution internally, so we'll have to think about doing that. Now, how would I approach this problem? I think the simple approach would be, well, I'll just find all the nodes in this tree, and then I'll compare them all. Unfortunately, that's going to be an O of n squared operation. I think that's going to be too slow for this. Ideally, we'd be able to go through all the nodes just once and say, have we seen this node before? So in that case, we need some way to identify the node that's not just the node on all of its subtrees. We need some, essentially, hash value for the node. So we want to find some value that just identifies the node without having to compare the nodes directly. So I like to call this the fingerprint method. If we had a fingerprint for the node and we can compare fingerprints, then we can find out if two nodes are the same without actually having to check all of their subnodes directly. All right, so let's do that. Let's come up with some function that gives us the fingerprint of a node. Okay, so what would this be? There's lots of different options for this one, actually. We could have a tuple, we could have an array, we could have a string. I think for now, we'll use a tuple because that will be the easiest one to compare. Okay, so our fingerprint will be, let's see, we'll just return a tuple of the fingerprint of the left node, then our node, and a fingerprint of the right node. So this should give us some unique value. Now, we do need a base case for this so we don't keep going forever. And that will be if the node is none, we'll just return none. There's no fingerprint for a none node. Otherwise, we'll return a tuple that's the fingerprint of the left node, the node's value, and the fingerprint of the right node. So now that we have something that identifies our node without actually having to go through a direct comparison, we can basically just keep a map of our fingerprint to the count of that fingerprint. So let's do that. We'll make it a default dictionary of ints, so it will start as 0, and we can just add to it as we go. All right, now we actually have to go through every node. So I'll do this the slow way first for example purposes, and then we can see if we can speed this up. So how do we go through every single node? Well, I like to do that with a queue. And we'll start with the root node in the queue. So while we still have a queue, we'll pop a node out. If this node is none, we can just keep going. Otherwise, we'll get the fingerprint for the node. We'll increment our fingerprint count. Then we'll check to see, is this a duplicate? If this is a duplicate, then we can add it to our result. So now I'll need some result, which I haven't created here. So let's do that. The result will be an empty list to start with. Now, if our fingerprint count is 2, that means it's a duplicate. We'll add it to our result. And now we need to add the left node and the right node to our queue so that we can process those. Okay, and I think that should do it. So while we still have some nodes in the queue, we'll pop one out if that node is none. So that could be if the left or right node gets pushed onto this queue, but they don't exist, then we'll just continue. Otherwise, if we have a real node, we'll find the fingerprint, we'll increment the count of that fingerprint in our dictionary here. And then if that count is 2, we know it's a duplicate and we'll append the node. If it's greater than 2, it means we've already detected that this is a duplicate. We've already added it to our result. We don't need to add it again. Okay, and then we'll push on the left and right nodes for processing. And that should be it. And then we can return our results at the end. Okay, let's see if this works. That seems to work. Let's see if we can pass all the tests. We do pass. Hey, and look, we did all of the February 2023 codes. All right. So we passed, but we only beat 5.2% for runtime and 5.9% for memory. So this works, but it's not a very good solution. We got some time left. I'll see if we can fix this up a little bit. So this solution still goes through every node individually, finding the fingerprint, which is a recursive call. So for example, the root node will find the fingerprint for itself, which we don't really need. We already know that the root has to be a unique tree. But regardless, we're going to find that fingerprint. And in finding the fingerprint, we have to find the fingerprint for all the lower nodes. Then when we go to the lower nodes in our queue, we're going to find their fingerprint. But we've already done that. We're going to find it again. So essentially, we're doing a lot of extra work. Now, one thing we could try, now I haven't tried this, so I'm a little bit nervous it's not going to work, but we can try to keep some dynamic programming value here. So let's see, let's have a DP. So with dynamic programming, essentially we will keep track of the input and the output to a function, in our case, the fingerprint node function. If we get the same input multiple times, then we don't have to actually do the calculation. We'll have the stored return value in our DP, and we'll just return. So if node is none, we'll still return none. Otherwise, let's check our DP. Now, this might not work because node will have to be hashable, and in this case, it might not be hashable. And any place we had a return, we'll just replace it with the DP node. And now we'll return DP at node. Okay, we'll give this a shot. I'm not convinced it's going to work. It really depends on whether or not node is hashable. Okay, it still works. So let's give this a shot. Okay, so yep. This should save us a little bit of runtime at the expense of a little bit of memory. Okay, we actually do a lot better in both. Well, not a lot better, we do better. So we get 12.3% for runtime and way better in memory, 91% for memory. So that was a good change. Okay, what else can we do to speed this up? The thing that jumps out to me is with going through every single node this way, we're essentially saying calculate everything for every node and then do the comparison. But we already know the deepest nodes are going to be, let's see, how do I put this? We want to process the deepest nodes first because the upper level nodes depend on the deeper nodes. So if we've already done that processing, it's going to reduce our processing of the upper nodes. Whereas if we go from top down, our upper nodes will process by processing the lower nodes, but then when we get to the lower nodes, we're going to be processing them again. So if we can change this to be a depth-first search, I think that will save us quite a bit of processing. So let's see if we can convert this to some depth-first operation. We're already sort of doing depth-first when we do this fingerprint. Okay, so let's convert our fingerprint node to actually keep track of the counts as we go. This is not generally great programming practice to have a function that does multiple things, but in our case, we're just trying to gain a little runtime improvement. So let's see what we can do. All right, so let's move this out here. And we can just get rid of all of this. Okay, again, if we don't have a node, we'll still return none. If we do have a node, we can return the DP of that node. But let's also grab that and increment the count. So in this case, our DP, our fingerprint, is equal to the DP of this node. And now we'll increment our fingerprint count for that fingerprint. And then we'll still return our fingerprint here. And since we are incrementing our count, we might want to do our check here too. So if this is equal to 2, then it's a duplicate, and we can add this node to our result. Okay, otherwise, we'll still need to go through, calculate the fingerprint for left and right, then put that in our DP, and then we'll have to do all this again. So let's do that. Okay, so it looks a little bit uglier than our other code, but I think this might give us a little bit of runtime. Oh, and that doesn't work at all. Yeah, it helps if I actually call our fingerprint en route to begin with. So again, this is not great coding, just because this function does multiple things. But let's do this. Okay. Let's see if this works. We are doing great for memory. We're beating 99% for memory, but only 11% for runtime. So this does work, but it doesn't really get us the improvements I was hoping for. All right. There are definitely things that we can do here. This code looks exactly the same. Let's break that out into a function. Let's call it register fingerprint. And it's going to take a node and the fingerprint. So this register fingerprint is just a way to break this code out because we're duplicating code here. So let's just call register fingerprint. And we'll pass in the node and its fingerprint. And so what register fingerprint will do, it will increment the fingerprint count, and then if our count is 2, it will append that node to the result. And so we can do a little bit of code cleanup here. All right, that looks a little bit better. Let's try that. Still works. Let's see if that saves us anything. Probably not, because it's an extra function call. Now we're beating 100% for memory, which is awesome, but only 12% for runtime. So for the runtime, one thing we're doing is we're calculating this fingerprint. Now this fingerprint is a tuple, and it's going to have to do some comparisons of tuple when we try to put it in our dictionary here. It might be better if we had some other value. I just chose tuple here because it was a simple one to understand, but we can make this anything we want. We can make this a string, we can make this, yeah, we can make this anything. So let's make this a string actually. We'll put node and then left and then right. And nothing else needs to change. Let's see. Still works. So now we'll be doing a string compare instead of a tuple compare. Might be faster. Oh, it might not work at all. Let's see. Oh, it's got this null in the middle. Let's move our node to the front here. All right, will this save us anything? Probably not. Oh, that actually makes a huge difference. Now it crushes our memory. We go from 100% down to 17% for memory, but we're now beating 91.4% for runtime. So I will consider that a win. It's definitely a trade-off. You always have a trade-off between memory and runtime. In this case, we're gonna drop our memory down to 17%, but our runtime is beating 91%, which I think is pretty good. Okay, well that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something. Try this one on your own. This is LeetCode 652. If you like this, please give it a like and check out all my other videos. All right, that's it for me. Hope you had fun, hope you learned something, hope you can go out and write better code.